All right, so homework number 10 is due on Wednesday, and we're going to talk about weirs today. I think the last couple of problems on that homework assignment will be addressed by the formulas that you see in class today. And then for the exam that we're having on Wednesday, remember that you don't need to bring your computer. There isn't going to be any question with Excel or with water gems, but you should prepare some sort of reminder sheet or formula sheet, anything that you'd like to supplement the equation packet that I've provided on Blackboard, and I'm going to print those out and bring it for you on Wednesday. And then on Friday, our class meeting will be online. Alex?
What classes will the exam be through?
It will be through and including today's class. Yeah. So since the first exam up to and including today. Now, since I'm a nice guy, I'm not likely to hammer home with really complicated and lengthy problems related to examples that you're seeing for the first time today, right? But
last class, you don't.
Exactly, right. Yeah. Other questions?
Is it only computational as well?
Yeah, there's no short answer questions. I'm not going to ask you to write a paragraph about the history of the OG spillway or anything like that. It's just calculations. Anything else? Okay. Here's a map that shows the Columbia River system in the Pacific Northwest. One of the unique things about the United States is that we have a really extensive network of navigable rivers inland. Of course, here in Huntington, we're adjacent to the Ohio River, which is feeds into the Mississippi River, which is joined by the Missouri River, and you can get to most of the Midwest through the Mississippi River system. But even up in the Pacific Northwest, an area that we usually think of aside from the coastal areas, which are wet, but when you get further east of these coastal areas, it's pretty desert and dry through Idaho and eastern Washington and Oregon, but still much of the agricultural areas here in the Pacific Northwest and definitely through the Midwest have access to really inexpensive shipping, where if you're hauling something that's very heavy and bulky like corn or coal or other agricultural products, one of the things that can give you a distinct competitive advantage is if you're able to move your freight for just a really low cost. And waterways do that better than rail, definitely better than truck. The only thing that's slightly more efficient than anything than waterway is pipelines. And there's plenty of things you can't ship by pipeline. You can't ship coal by pipeline. You can't ship soybeans by pipeline. Only liquid products, obviously. So navigable waterways are part of the reason why the United States is just consistently at an advantage against other countries that have productive agricultural areas but not as much access to cheap transport, where throughout Europe, for example, the agricultural products that they have to grow, most of it is moved around by train. That's part of the reason why we don't have a very good rail network in the United States, at least when it comes to passenger rail, is, we have a fair rail network in the U.S., but there's just so much of the cargo that moves around by shipping that it makes it less necessary than it otherwise would be. So here the Columbia River is navigable all the way to Lewiston, Idaho. So it's hundreds of miles inland. And we're going to be talking about some of the hydraulic structures today that makes that possible. Of course, it's dams, but what we do to regulate the flow of water through a dam is with spillways and weirs. And so we're going to be talking about some of the formulas that describe the relationship between water depth and flow rate over those hydraulic structures. Just to put the magnitude of the Columbia River into perspective, the dam, the Grand Coulee Dam, has the capacity to generate more than 6,800 megawatts of electricity. That's really a lot. I mean, to put it in perspective, here in West Virginia, we have a very large coal-fired power plant, John Amos, which exports power, it provides power to West Virginia, but it's also exported to Pennsylvania, Ohio, and other surrounding states, depending on demands in the grid. But the John Amos power plant has a capacity of 2,900 megawatts. And so in terms of hydropower, this is one of the biggest facilities in the United States. And so it's a really significant contributor to the economic viability of places like Seattle and Portland and other cities in the Pacific Northwest. So the Grand Coulee Dam, most of the time water isn't flowing over the top of the dam ordinarily, because if you do that, you're not capturing any electricity from it. You can only get hydropower when the water is flowing through an enclosed conduit and then comes in contact with the impellers of a turbine. And so ordinarily most of the water is going through what are called penstocks, which is these large diameter pipes that carries water from the dam and then down to the receiving river. But occasionally the flow rate into the reservoir system is so high, because there's been storms in the watershed, that they have to send water over the top, over the spillways. And we've talked about spillways before in California. Remember the spillway damage that they had at that dam in California that caused quite a lot of risk to the people downstream. There was the possibility that the dam itself could be threatened. But the slope of these spillways is designed to help dissipate energy, because the river downstream could be really badly damaged and scoured if the water, which is falling hundreds of feet and is picking up a lot of energy as it falls, is just left to flow at a high velocity. And so they're intentionally designing these spillways to try and cause a hydraulic jump downstream and try and control the location where that energy is released, rather than having a high velocity and the scour potential downstream. But all of this is tied into the idea of weirs, the shape, the length, the height of the weirs. And so let's watch a brief video that explains some of the basics of the weirs, and then we'll look at the equations and do some calculations on our own. Unfortunately, I think we're going to have to probably suffer through a commercial here. Okay, yeah. Old Spice, those are always interesting, right? Okay. Now you're getting hungry. So I think that video does a really nice job explaining the basics of weirs, and I know that some of you are taking environmental engineering this semester. Have you talked about clarifiers so far in environmental engineering? No.
I took it already, and I don't even remember.
You don't remember clarifiers? Okay. Well, when water is being treated, it has things that need to settle, whether it's drinking water or wastewater. Things that need to settle to the bottom. And so there are these tanks that you've got water in it, and then there's basically an overflow where you're taking the clean water out, and then the dirty water is collected off of the bottom. And there's all these little particles which are settling downward in a clarifier, and they're so small that it's easy to disturb them. If the water that's going out is being removed at too high of a flow rate, what it does is it sucks these particles towards the outlet. And so you have to remove the water out at a really low flow rate. You need to have a low velocity, that is. And so, in the video, it talked about how if you've got, this is like our circular clarifier tank, we're looking from a top view. This other one was a side view. So if you are looking down from above, ordinarily the way that these clarifiers would work is that the water is coming in through a pipe, and then it's kind of going out across the top, and then it's flowing outward towards the edge. And so there could be this distance around the edge that's basically the weir length. In the formula, it was telling you that the length of the weir is one of the important parameters that dictates the flow rate out. And if you only have a relatively small length, then of course velocity is it's the flow rate Q divided by the cross-sectional area. And the cross-sectional area that we're talking about is the depth of the water and then the length of the weir. So that same trick that it was showing with the folded weir is used in clarifiers, where instead of just a single flat weir surface, what they would do is they would have a zigzag pattern that basically increases the length, where the total length would include all of those ins and outs. And so that sawtooth pattern is one of the tricks that they use in wastewater treatment to increase the area, and then that decreases the velocity. So this has application not just to water resources, but also to environmental engineering as well. So they described the most efficient shape for a spillway to be the OG shape, and it's kind of, some people get the reference, right? Yeah. So OG, I was wondering, like, why the, it's actually O-G-E-E. So it comes from the Latin root that means, like, it's similar to apogee, if you've ever heard that word, meaning like the top point of a curve. And so it's just a certain curvature shape that applies to this because it mirrors the shape of the water. If it has some forward velocity and then it's falling as it goes over a sharp-crested weir, then the water that's tumbling down the face of the spillway would follow this shape. And so if we want to accommodate the highest amount of flow rate possible, if you want to have a big flow rate Q, then you'd follow this OG shape, and then it would minimize the variation in the water height. And they made a pretty good explanation in the video on, oh, by the way, did I start the recorder again? Yeah, okay. They had a pretty good explanation in the video on the reason why you don't necessarily want a lot of variation in the height of the water level above the spillway. It could be that there are homes or that there are docks upstream of the spillway, and a wide variation in the water depth is going to make it more challenging for boats to put in. It could potentially threaten structures that are along the shoreline, and so we want to try and have as much availability in capacity. You want to be able to convey as much flow, Q, with a minimal variation in H for the given length of the spillway. So this parameter L is talking about, for example, the length, which would be this distance across the top. And you can see from this photo that they have the same thing that was demonstrated in the video, that these gates could be opened and closed independent of each other. So if there is water going over the spillway, you don't necessarily have to have all of the gates open to do that. And that gives them some additional control over the height of the water in the reservoir, is that they could allow the water to pool pretty high and only open up one gate if they needed to, but they could open all of them and accommodate a big flow rate with a minimal adjustment to the height. So what's built into this number here, 3.32, is both coefficient of discharge, which is related to friction loss, but then also some conversion parameters related to the gravitational constant. And so you'll see when we're talking about the Sharp-Crested Weirs that a similar thing occurs, where we can combine a couple of discharge coefficients together into just a single parameter that's at the front. But these are dimensionally non-homogeneous equations. And remember that what that means is you don't necessarily get the same units on the left-hand side of the equation as you do on the right. So think about Q would have units of volume per time. For example, like cubic meters per second or cubic feet per second. Whereas on the right-hand side, you've got length, which would be meters or feet, and then another length term that you're taking to the 1/2 power. So you're not going to get cubic meters per second on the left-hand side equation, those same units on the right-hand side equation. The the conversion factor or the empirical observation factor that brings it all together is here in the coefficient in front of it. So you can see that the formula could either be in terms of H, capital H here is the height above this theoretical sharp-crested weir to the water level upstream before the drawdown occurs. So you wouldn't measure H or H sub D right at the structure itself, because as the water approaches the spillway and begins to accelerate, it's drawing down the water surface. So you have to go some distance upstream before that acceleration has begun to draw down the depth of the water and measure either H or more likely H sub D, since that's a physical parameter. You know, it's the actual physical elevation of the spillway crest up to the water surface, and then put that into this formula to get the flow rate. So let's think about how this may fit together in the real world. I'd like to pause for a moment and let you calculate this example where what we've got is a 300-foot long spillway. And so this distance 300 is the length parameter, that's the distance into the page that we don't see. So if it ran really long, 300 feet would be that spillway length. And what we know is that the water that's coming into the reservoir that is caused by this dam is when there's a 100-year storm, which 100 years is just referring to the relative infrequency of that storm. It's a storm so large that it's likely to only come around on average once every 100 years. And probably the more precise way to put it is that in any given year, there's a 1 in 100 chance of that storm coming through. So in any case, the flow rate's 38,000 CFS. That's the flow rate that we'd see for this design storm. And what we want to know is what is the elevation of the spillway crest if we want the water level to not go any higher than 4350. It could be that there are some homes or other structures upstream. We want the water level to never be any higher up than 4350. So to achieve that, what should the elevation of the spillway crest be at? So you can see if we know the flow rate and you know the length of the spillway, what we're going to be solving for is how high will the water level be above the spillway crest for that flow rate.
British gravitational units.
Yeah. Yeah, so two good questions come up. So the first is that this is the formula for traditional units. So there would be a different one for SI units. Now the other part is that when you have an OG spillway, there isn't actually a sharp-crested weir there. Sometimes for modeling purposes, we would try and express this OG spillway in terms of an equivalent sharp-crested weir, but what we want to know is, in this example, it's asking like the actual spillway crest, what elevation should that be at? So you need to solve for H sub D to solve this example. We're not trying to know H, we're trying to know H sub D. Okay, so we can rearrange the equation and see that in solving for H sub D, which is the distance from the spillway crest up to the water elevation, some distance upstream before the drawdown occurs, that it's going to be a distance of 10.06. And so that hasn't yet answered the question, though. That says we want the water level to be at 4350, and so the spillway crest should be 10.06 feet below that. And so if we want to know the elevation of the spillway crest, we should build that 10.06 feet below the maximum height that can be tolerated. So that would be 39.94 feet. Did anybody else get that same value? Yep. Okay. So pretty straightforward in this case. Any questions about the example?
So the flow rate would have to be the maximum design flow rate, correct?
Yep.
Because if you're looking at the maximum depth.
Right. Yeah. So if the flow rate coming in is larger than that, that would increase H and begin to flood the structures that we're trying to protect. If the flow rate is less, then it's just simply H sub D wouldn't be as high. So there would be less of a height over the spillway. Or it could be that, you know, the spillway is only used in emergency situations. It could be, in this example, that there's that same penstock or, you know, non-spillway ways of having the flow go through the dam. All right, so that OG spillway is one kind of weir. Here is a broad-crested weir. We've talked a lot over the last couple of class meetings about obstacles put into the channel. Remember how we've said that, you know, water's flowing through a channel under steady and uniform conditions, and then there's some obstacle. And the water has to pool upstream over the upstream of the obstacle until what?
It's enough energy to flow over the top or around.
Until there's enough energy upstream of the obstacle to flow over the obstacle. And so here you can see that enough energy has accumulated so that now the water is flowing over the obstacle at the most efficient depth. So at the critical depth. Now this is a relatively narrow broad-crested weir. It's not very long in terms of following the distance of the flow. So there's a little bit of drawdown both from the upstream side and the downstream side. So like, where is it the critical depth? I think it's what you'd usually see is about the depth about halfway in the middle. Before the drawdown starts to happen, you'd measure the critical depth there. But the point of these broad-crested weirs is it's a way to measure the flow rate. If you have some obstacle where the height of the weir is larger than the maximum that can be tolerated without causing pooling, so you exceed the delta Z max, then you're going to force critical flow over that obstacle. And it can be a means of quantifying the flow rate. Now the disadvantage of something like this is that when you put an obstacle in the bottom of the channel, it can accumulate sediment and other trash and debris on the upstream end. And so when the water is flowing and maybe the bed load, meaning the gravel and the sand and everything that normally would flow at a slow flow rate at the bottom of the channel encounters this obstacle, you can have an accumulation of sediment and debris upstream. So that's one of the big disadvantages of a broad-crested weir for measuring the flow. And there are ways around that using other types of devices to measure the flow, but these are an important tool to quantify the flow rate. And I mean, the way that they work from a calculation standpoint is that you induce the critical depth over the obstacle, and remember that the critical depth represents 2/3 of the specific energy when you've got critical flow. And so if you have the critical depth and then some sort of an energy loss coefficient, so C sub D is just representing how much energy is lost when you have an obstacle in the way. B is the width of the channel and the width of the weir. We can use this formula to estimate the flow rate through the channel. And you can determine the coefficient of discharge, which is, again, how much energy is going to be lost as the water goes over that obstacle, by looking at the ratio of the weir height and the amount of energy that's in the channel, so H. So these broad-crested weirs are one way to quantify flow. A sharp-crested weir is another. So this sharp-crested weir is different in the sense that we're not necessarily trying to cause critical flow over the obstacle. It's just an obstacle that has caused pooling upstream that ordinarily wouldn't have been there. And what we can do to try and figure out what's the relationship between depth, H, and the flow rate is consider the energy before the drawdown occurs. Here at location 1, how much energy there is. It's the depth above the bottom of the channel up to the weir, so Z, and then the distance above the weir height to the water surface, Y. And if we want to know the total energy, so TEL is total energy line, then we'd also account for the velocity head, V squared divided by 2G. So if you look at the energy at 1 and compare it to the energy at 2, there's been some changes. So in terms of specific energy, we look at the height of the water above the weir, so y1 and the velocity head, and when the water is approaching that overflow, it's increasing the velocity and it's losing the depth. And so whatever y1 term was there at location 1, the elevation above the weir, has been exchanged into extra velocity at 2. So we can rearrange that and just say here at the location where the water elevation is the same as the weir elevation, where there's no y2, then we'd solve for the new velocity downstream. That faster velocity would be the original velocity plus the effect of how much energy had been gained as the water elevation is going down. And interestingly enough, what we end up with is the same formula for the velocity at 2 as the orifice equation. You may remember from fluid mechanics that there was a question of what happens when you've got a tank with a hole in it and water is flowing out of that tank, and what you would do is you'd measure some distance from the water surface to the center line of the orifice, and then the velocity out is the square root of 2gh, where h is the distance from the water level to the center line of the opening. So this orifice equation was a way for you to know what's the velocity of the water as it comes out of an orifice. And the same thing is true here, that here what we're saying is the h that we're representing is the total energy. And here, in the case of the orifice equation, the energy was only the height of the water. In a stagnant tank where the water isn't flowing, there's no velocity head. But in this open channel where the water is moving, h does include the velocity head. So it's the depth, y1, plus the velocity head. So if we know those two things, then we can determine the velocity at 2. And so it's all of that together that gives us these equations for relating the flow rate to the height of the water above the weir. So let me walk you through this formula, which is going to itself be simplified a little bit later. C sub d is again a discharge coefficient that accounts for friction losses, and also in some cases the water is having to contract because the weir may not be the same width as the channel. I'll show you an unsuppressed weir in a moment that has contraction, but there is drawdown. Drawdown is as water is approaching this weir, it's accelerating, and there's some energy loss as it's in contact with the edge of the weir. So all of these factors mean that we're losing some fraction of the specific energy that was upstream compared to what's downstream. And then 2/3 of the square root of 2gh, where what we need to do is ultimately combine together the 2/3 and the gravitational coefficient. But the width of the weir here, this term L, also is a factor of how much can be accommodated. And this is the formula now that was shown in that video, where they were saying it's a C value, a length, and the height of the water above the Sharp-Crested Weir to the 1/2 power. So the C value that's here is just combining together the 2/3, the square root of 2g, and then also for a typical discharge ratio. If you're estimating the discharge coefficient based on the ratio of how high the water level is to the height of the weir, ordinarily we wouldn't have a really big h relative to z. So for typical values of a relatively small h compared to z, then the typical discharge coefficient under most conditions is about 0.62. So if you combine all of those coefficients together, then the Weir equation would have a prefix coefficient of 3.32 for traditional units or 1.84 for SI. And then you could put in the length either in feet or in meters, and then the h term would be also a distance in meters. And h, remember, is how far is it from the weir up to the water surface. And this water surface that you're measuring from the side view is before the drawdown occurs. So H, if you look, is going to include some amount of velocity head, but typically for slow-moving flows, most of H is just the depth itself. And so sometimes when people are being a little bit fast and loose, they won't bother to calculate the velocity head, and they'll only measure the depth of the flow and put the depth of the flow into this formula. But more specifically, H should include the depth of the water plus the velocity head to be completely accurate. Now this is the formula for what we call a suppressed weir. And just to illustrate what a suppressed weir is, if you have water flowing through a channel, so this is a top view, and the water's going downstream, and then here's the weir, and the weir is the same length as the channel. So like the Sharp-Crested weir is the full width of the channel, then we call that a suppressed weir. But if the weir is only like in part of it, and the weir is maybe just the blue section in the drawing, this would be called unsuppressed. And we have to make a correction in the case of an unsuppressed weir. So if you have a contracted rectangular unsuppressed Sharp-Crested weir, there are some edge effects as the water is beginning to approach the weir. If it's flowing through the channel you've got velocity the entire width of the channel, but then it's having to approach only part of the channel width has the weir, then the water's having to change directions right in front of that weir. So it's kind of showing this ineffective flow area around the edge. And so we basically, even though L is the length of the weir and not the width of the channel, so note, B is the width of the channel, which is independent from L in the case of unsuppressed. You still find the effective flow area with L prime, and subtract out this little edge that isn't going to have much flow through it because of the contraction. So that's just the one correction. I think that you may have a homework problem that distinguishes between a suppressed weir and an unsuppressed weir, where the length of the weir is different from the channel width. So any questions about suppressed versus unsuppressed?
Is that what like creates an eddy in a river?
Yeah, it's one of the things it can, is the contractions. Okay, now before we go our separate ways, let's take a look at the schedule and briefly talk about what is going to be included on the exam. So here is the schedule for the semester. Okay, so we had our first exam on Wednesday, February 22nd. And remember that the first exam is worth more than the second exam because it covered more lectures. Exam 1 was worth 18% of the grade, whereas this exam that you're going to be taking on Wednesday is only worth 14% of the grade because it's a relatively smaller part of the course. Okay, so that said, there was channel geometry, slope, channel flow. So one of the things that we talked about in that section was the definition of shear stress, and we talked about how Manning's N was developed, the equation for steady uniform flow. You know, how to find the depth for steady uniform flow is Manning's equation, and the derivation of that is just understanding that there's a shear stress that's applied by the channel to the water. So if it's been a while since you went through the trapezoidal geometry, it could be worth your time to refamiliarize yourself, for example, on how would you find an unknown depth for a trapezoidal channel where I've given you the flow rate Q. So I've given you the N value, I've given you the flow rate, the side slope geometry, and all you're doing is finding the depth of flow. Very often those types of problems will come up on the second midterm exam.
That's the one where you use.
Yeah, it's where you have to use a solver, right? Because we did it a few different ways. We did it with Excel. We did it with what's the name of that online
Wolfram Alpha.
Wolfram Alpha. You're not going to have access to either of those in the exam. So you'll need to solve for y using your calculator. Okay, now, aside from steady uniform flow, where you use Manning's equation, most of what we've been doing is specific energy analysis. So when there is a discussion of like how to find the critical depth or specific energy diagrams, chokes, whether they be a step up or a channel that's getting too narrow, all of that has to do with specific energy analysis. And that goes to solving for the roots of a cubic equation. So that would be the other kind of like quantitative thing to practice before the exam is, can you solve for the depth in a trapezoidal channel, and then can you reliably find the 3 roots in a cubic equation? So that's going to be our exam. It's going to be lectures 20 through 30, so including today. Any questions before we finish up for today? Well, all right. So I'll see you then on Wednesday. If anything comes up as you're studying, feel free to send me an email or give me a call on Teams.